Okay, I think now we get started. So today we have a very special guest from Ververica, Ben, and he's an absolute expert in the field of stream processing. And everybody, if you have any question about stream processing, um, today's the time to ask. Right? He's an absolute expert.
All I can promise is I
And
will try and probably fail to answer some of them.
yeah. First, I'll give an introduction to myself. Right? I'm Sida Shen. I am a product manager from CelerData. We're the company behind the StarRocks project, right? And Ben, do you want to give yourself a introduction? Who are you? What is Ververica? And your experience, with your history with stream processing.
Sure thing. So my name is Ben Gamble. I'm currently the field CTO at Ververica. When I say CTO, these days it more means Chief Talking Officer than Technical Officer. But my background in stream processing kind of really goes way back to my kind of first kind of career moves where I was working in image processing. So this was a stream of images on a UDP transportation from a specialized camera. And we were trying to do inspection, basically building inspection robots for manufacturing supply chains. And from then it was always a thing of how do you process a stream of data? Because the answer was always, I need this now, whether it was a machine to do a rejection on a faulty product. But then as time went on, I started dealing with more and more kind of like stream-based systems. For a long time, I ran a logistics company where we had continuous people asking for us to take a package from A to B, find like, well, where is the nearest van that can pick something up? Similar to Uber. And as you kind of take these challenges, the one thing that continuously comes up is you can't just wait for 50 orders and then process them, or doing a request response on an asynchronous web server. You always end up with the simple problem of how many things am I handling? And there's a famous saying which any sufficiently complicated C project ends up with a broken implementation of Common Lisp in it. And my argument is any sufficiently complicated microservice architecture ends up with a broken implementation of a stream processor somewhere. And I know because I've built that at least twice to date.
Yeah, that is great. That's great. So just to get everybody on the same page, there are probably people in the audience that are not familiar with stream processing, right? So Ben, can you just give a definition of what is stream processing?
So to me, stream processing is having the ability to act on a sequence of events as they arrive, either as themselves or as in smaller groups, but in a continuous fashion. And this is kind of an important point of like, there's like the term micro batching or nano batching is kind of orthogonal to what stream processing is, because even your network card does batching. It's called Nagel's algorithm. We do it for efficiency. So streaming in my case and stream processing in my case is all about doing it continuously. There's no stop start. There's no kind of, you don't stop stream processing to wait for a big chunk. No, instead you're continuously doing it. You might pull it in chunks for efficiency, but the continuous nature is the goal.
So if I'm understanding correctly, so it's all about triggering by events. It's always on, right? It's always incremental,
always on.
Right? Yeah,
that is the critical bit. So yeah, there's an ongoing kind of little thing, discussions in the communities where a lot of people are trying to look at these stream processing systems like Apache Flink, and there's a fun one saying, so how do I schedule it to start and stop? And the answer is you don't. You just leave it running, and as the event hits, you process it. And this is a bit of a shift to when you used to just wait till you had a few gigabytes of data, press a button, and it would churn through. Not to say that approach is wrong, but the whole point of a stream processor is you don't have to do that. You just leave it running.
I think a natural question to ask is, it's if it's always on, right, it must be pretty expensive, right? So how do you manage the cost? Is it actually that expensive?
So this is an interesting question, and I'm going to caveat this by saying this is both my opinion and your mileage will vary, because specifics you can always engineer a scenario where things aren't true. But let's take the general case. Let's say you have orders to process. There's shipping orders. You're on an e-commerce website. Most of us are secretly e-commerce websites. Behind the scenes, we have people online buying stuff. So an order comes in and you want to process it. So the next thing you have to realize is, let's say you want to process this in a big chunk, every 5 hours, every hour. every day, right? So the first thing you've got to do is take those events as they land, and then you've got to store them. As you store these events, you're paying to store them. Then when you've got a big pile of them, you're then spooling up enough machines to process them within the time allowed. This is currently a big thing that happens in banks when you have this kind of a reconciliation step at the end of the day. The bank closes transactions and then churns through on a mainframe somewhere and does all this processing. This is expensive because you now have to have machines big enough to churn the backload in the amount of time you actually have
backfill data, right? And
exactly.
And
Whereas,
batch.
That's the big batch. The flip side on streaming is the event hits, you process it as it happens. Yeah, you've got as long as you can take the throughput. So you now have to just say, I need to handle n events per second. And then as long as you can handle the throughput, you're only going to pay for the minimum amount of machines to handle that continuously. The two things about that are that one, if the job fails, you failed on one or two events at a time. It's not a big deal. You just restart and go. There's no big downtime. There's not this massive crunch where on a lot of older school systems, if you fail partway through a batch, you've got to restart the batch. So instead, your amortized cost is quite low. In addition, you can often use quite small machines because you can just have them continuously going. If your demand ramps up, of course you're going to need more, but you'd need more on your batch side anyway. The reason to stream generally comes down to this. You need an answer inside a time window. That's a given. That's your SLA, right? I take an order from you. You probably want me to come back within a day to say, yes, it's allowed. You don't want me to come back 3 weeks later saying, I've shipped it when it arrived, a week after you replaced the order. So you kind of there's always going to be that trade-off. You can make things incredibly cheap in either direction, but generally streaming tends to be quite cost efficient because one, there's no failure doesn't really cost you anything. All stream processing systems are built with this redundancy, retry, and all that kind of logic built in. Two, you pay for smaller machines and you amortize the cost over a continuous period of time rather than having to pay for a spike. And three, you're never going to be without that data. So you're not storing it in large chunks in every single step of the way. So you're not waiting for answers. You're not going to have to hold more inventory because you didn't process an order. So you can save in other places as well. So on balance, everyone has shifted to streaming to both increase outcome, the kind of the performance and value of outcome, but also because some of the older, bigger batch systems, right? They were really expensive because to handle, 300,000 records or 1 million records in a chunk requires a lot.
Yeah, that makes a lot of sense, right? I think a lot of the perception of, why streaming is inherently expensive, runs all the time, right? It's actually working on the same amount of workload as you were, run it at the end of the day, right? We'll run everything all together.
Yes.
But a benefit is, failover, right? If you have a big Spark job that fails, right? You have to redo the whole process.
I
right?
wish
but
I didn't know that so well as I do, but I've seen a few big Spark jobs go crunch, towards the end of the cycle and then have to go, oh no, what happened?
Yeah, some of it, has some of the failover built in, but not to a level that, with the stream processing tool, right? You can have checkpoints and you can always, retry a very, very small amount of work you have to redo if something actually fails, right? And it's actually the same amount of workloads as there, right? And also, there are a lot of questions at least in the StarRocks community, right? People look at stream processing and see it as a quite expensive, piece of tool, right? And how do I know if stream processing is actually useful for my business, right? Actually, the value overshadows, the cost. How do I know? What do you speak, to those kind of users?
Okay, so let's kind of the reason I always come back to stream processing is actually to stop looking at the business for a second and start looking at their customers, right? I think in most cases, nearly all businesses eventually serve either directly or indirectly a customer, a person who has to do stuff, right? And as a user and a consumer of goods, the one thing I know is that I don't like waiting, right?
Yeah.
Right? How is it good? One of my favorite things about Uber is I know how long that car is going to get to come here. If it's raining outside, I don't have to leave the house or the building until I know the Uber's ready to pick me up. And I know for a fact that like when I place an order on Amazon and I know it's going to come next day, I don't have to worry. These are all done because these are all possible because of stream processing. So the fundamental thing comes down to, if you're serving a user at any point in your system, whether it is a human or even worse, a machine that wants an immediate answer, you're always going to be limited by your slowest step in your journey. It's called Amdahl's law in programming, but it applies across the thing. The theory of constraint is the way it's often termed in manufacturing. So with stream processing as kind of a primitive to use at the bottom of the stack, there's less and less performance gates before you get to a user. There's nothing worse, particularly I find right now, as someone who has to fly around a lot, of I want to do something which requires an airline. The airlines always take hours to get back. It is painful. And I'm like unsure if my flight's booked, unsure if it's changed. And because they've not embraced streaming for various reasons, honestly, it's just the fact that they have such big systems, I think, and so much security, that I, as a user, have to pay the price of their previous technological decisions.
Yeah, that is true. But, the technology complexity, can you speak about that, right? So how do,
Yes. So complexity is an interesting thing. Like, show me a simple system which can drive an interesting and rich outcome, and I'll be very surprised. Like everyone thinks, oh, but it's simple. I only do X and Y. And then you think, okay, wait a second. Let's think what does simple really mean for a minute, right? Now, the running joke I always say is more people build distributed systems than they think, because a website requires your computer and mine, and we've already got a distributed system. So you think for a second, like, wait a second. What is actually simple? Because like most web things are built in minimum 3 programming languages as well.
Yeah.
And so that's kind of the first kind of obvious point about always poke about complexity. But the next step is, what is the alternative to, let's say, bringing in a Apache Flink style stream processor, right? So you start with the ability to absorb events. That's great. There's a series of web servers. Now they got to scale. Okay, cool. So I put a scaling group against that. Now I need to make them reliable. Ooh. Now I fail over. I need state stores inside the servers. I need multiple layers to dump events. Okay, so now that's nearly always true. So now the event system that go on the back of that. So I need to be able to take events out. I need to store them, process them in either small groups to do some level of aggregation. I need to be able to filter events. I need to be able to scale and then do fault tolerance on these events. I need to have a timeliness factor, measure the SLA end to end. I need to handle back pressure. And as I keep adding these kind of fundamental features, because everything starts simple, it's great on day one. Day one, you could spool this all up. I know I have. I had end-to-end microservices all streaming gRPC between them. It worked great. And then I basically kind of put it into production, and it worked fine. And as I put more and more load, and I had clients who also had SLAs, I had serious problems, because as they rely on my SLA, right? If I have a problem, I need a system which is tolerant, which can handle that kind of fault tolerance, because I can't cascade that up the tree. I have to meet my contractual SLA. So I end up having to engineer things like failovers, things like checkpointing. And fundamentally, like, why should I be wasting my time building that on day 1 or day 2 or even day 50, when I should have almost thought, I am now doing stream processing. Should I have brought in a stream processing engine?
Yeah, you always use the right tool, right?
Exactly. Like, this is the kind of the big thing right now, is we'd all love enough time in engineering to go and build it all from zero, right? It would be wonderful. We could guarantee it works. We could build a system tuned to the outcome we needed. However, show me, you're a product manager, tell me the last time you had enough time to build it exactly as you wanted.
Yeah. This
Never.
There's no.
There's always a trade-off. And we only have this kind of amazing technology because we're willing to lean on other systems. And the kind of challenge I often give to both my customers and other people I work with is, are we leaning on the right bits, right? Like, everyone leans heavily on gRPC because it's a very nice RPC system, but the streaming bits are bolt-ons. So it's like, why would you use a bolted-on streaming thing rather than a specialized streaming service?
Yeah. It all depends on the kind of workload that you're trying to run, right? And
exactly.
Always try to pick the right tool instead of the one that actually looks easy on the day one, but actually gonna when you go to production and try to scale, it doesn't work. Right?
Yes.
True streaming is inherently easier to scale, is it?
So this is, I'm going to say yes, and I'm going to provide a little caveat here, which is that scaling a system which can act continuously on events is how batch systems are scaled as well. So inside any batch system these days, right? Hell, inside StarRocks, right? You have your data is streamed from disk into the backend services that do some of the crunches, then streamed to the front ends. So you can do these massive, petabyte queries. That is streamed already. So even if you're doing that, and that's like a one-shot analytical query, sounds like classic batch, right? No, it's streaming now because it's too big. The only way to get performance is to stream. The only way to handle very large systems and very large data is to stream.
Yeah, actually, when we do aggregation, we do a streaming aggregation whenever we can, right? To to not have like a hash table is too big, it doesn't fit into memory, right?
Exactly.
So we actually use that is a fantastic point you just brought up. I mean, a lot of us are already using streaming without actually knowing it. So it's not really even that scary of a subject, right? Because we already have them in our production system, isn't it?
Exactly. Like I remember it was a different podcast, and Hannes, the creator of DuckDB, was talking, and he was pointing out that every single operator in DuckDB streams between them, right? And I was like, really? And then I went into the source code and looked at it, and I was like, wow, that's really quite cool. And then I remember reading the StarRocks source code the first time around. I was looking at how it sent data between operators, and I'm like, this makes sense. I now don't need a petabyte of RAM on my cluster. I have, in past lives and past jobs, and systems I can't fully talk about, but there were systems where you needed enough RAM to hold the whole data set. Some of those very fancy dashboards of yesteryear required, hundreds of gigabytes of RAM to run, because they're the only way you could do slicing and dicing in real time on a dashboard.
Yeah. So streaming is just to summarize a little bit, right? So streaming is not as scary as it looks like, as the word looks like. Streaming does give a lot of value, but there are already many systems that we're using. You guys are using in production that are already streaming things around, right? Without you actually knowing it. So with the technology that are available today, right? So what use cases can stream processing specifically excel in, right? What kind of use cases are there, for stream processing? If you can shine some light on that.
So I can say there are as many as we could invent, but let's just focus on a few to start with, and we'll see where it goes from there. So I'm going to start with one of the more obvious ones. So currently we're on a live stream, right? So there is connecting us to each other and to our audience right now there's a WebRTC stream, which is called real-time. I've forgotten now, but I remember when it was being launched because I was part of that team. Now, the WebRTC feed is a UDP stream of audio and video, and that's going through. There's a little bit of, and the processing you can see already on that is there's a blur on my background, and there's a blur on Sida's background. Now, that's part one. Part two is there's a chat here, right? The chat is an ordered sequence of messages coming from a lot of users being collated together and then being broadcast back out. This is done using real-time stream processing for many reasons. The first one is to be timely. Humans like to talk in a very synchronous fashion, right? But it's an asynchronous but synchronous. I say something, you say something, I say something, you say something. And although we can talk over each other, we make it feel synchronous. Now, the problem is that if it takes too long for that message to get back and forwards, right, the delay increases because of I send a message, you wait 3 seconds, then you send a message and I wait 3 seconds to hear from that. And it might take you 2 seconds to write it. That's a 8-second delay already.
Each interaction is adding up to the problem.
Exactly. So unless you're doing it continuously rather than batch send, you're going to end up with a terrible user experience to the point of where it loses all potential value. So chat is a big one. Now, it gets more interesting when you start having large numbers of people and you want to do moderation, because in a forum, in an open forum or one in the public space, you want to be able to filter out basically you want to filter out hate speech, you want to filter out anything harmful to the audience at large, because it's not fair to impinge someone else's experience. But also it's just a professional space, so of course we filter out tons of things. And I've definitely seen things where the competitors' keywords are often filtered out in some chats. It's very funny when you see that happen. But the next thing is, of course, is chatbots. So these are things that aid us in some way. Those are
Yeah.
things that have to act on a continuous stream of data, stream back results. It's all well and good to have a lovely AI agent somewhere, but if it took 5 minutes for it to come back, I'd get bored and go off the tab. That's
Yeah,
part. That's
I
one of the
think,
ways.
yeah, I think this is really interesting. I mean, the audience we have, we work on analytics, but stream processing also works in transactional systems, like you
Yes.
mentioned, right? Yeah. So, and what about in analytics, right?
Oh,
What
yes.
kind of
So
use cases, does it power?
yes. So I as you may have realized, I come from the transactional background. My background has always been like lots of like things like payment systems,
Yeah.
security systems, games, logistical things, logistics, where I literally was pick up a package, move a package, find a route. Now on the other side, I have of course worked into the real time kind of analytics, and here is where stream processing almost kind of like both comes into its own, but it's also one of like the most straightforward ways to add value. So this is something like this is when you start asking the questions of your system. And like transactions is how you ask your system to do something. Analytics is how you ask questions of your system. So in this case, it's something like, how many transactions are we doing per hour? Can we afford to keep going at this rate? Are we going to run out of nuts and bolts in our car making factory? Should we slow down upstream production so we don't end up with what's known as work in progress? These are analytical questions because they require a look across more than one data point at a time. And
Yeah.
this is the ability to say, I've got every single sensor streaming in. Are any of them exceeding a threshold of temperature for more than their standard tolerance? Or I've got people checking in rapidly right now at the airport. I'll be doing that later myself. And are we going to have enough people on the security gates to let people through? Do we need to open new
Yeah.
security gates?
Yeah. Yeah. So basically summarize, something like monitoring, right? Where the data freshness requirement is literally like
As
milliseconds
fresh as
or 2
possible.
seconds, right? As
Yeah.
fresh as possible for the machines, right? Or, for those
Well,
like customer
actually,
facing. Yeah.
I'm going to challenge on this one, right? So this is where the term real time gets thrown around a lot, right?
Yeah.
I'm sure you've heard I've used it. You've used it.
Yep.
Can I get a thumbs up in chat if you've used the term real time and had a different person say that's not real time? Because I definitely have.
Yeah.
And so real time, in the context of where we're from, at least right now, is what's often termed soft real time. This means as fast as possible in commercial off-the-shelf situations, right?
Yeah.
There are no specialist hardware, maybe some cool software. We like cool software, but generally nothing is deliberately. Oh yes, bag check. Yeah, Heathrow bag check is quite terrible. I'm sadly too aware of this. I feel your pain. But back to what real time means, right? Now, real time could mean hardware chips with what's known as a watchdog timer and a hard requirement to be within a few microseconds either way. In our world, it means our P99s are good. And that's about it, to be honest. And beyond that, we probably agree a nice SLA to our customers. But we agree the SLA in terms of, you gave it enough compute, right?
Yeah.
Right? You did give it enough CPUs, right?
Yeah, that is true. That is true.
Near real time is sorry, to answer the question here from Christopher. Near real time is a fuzzy one, right? The only reason I prefer soft to the near is because of like hard real time does not mean immediate. It means you define the exact SLA with real boundaries and real statistical probabilities.
Yeah.
Just to give an example, I used to build like manufacturing equipment, and the tolerances, and like we had a cutter that cut paper labels, and that had a real-time requirement on it, and that was an exact 100 microseconds one way or the other, but it was always within that exact tolerance. That was real-time or hard real-time. The reason I don't call what we do near real-time is because we might come back in less than 100 microseconds. That's not a problem. I've worked on real-time where real-time is a second, but plus or minus a few microseconds.
Yeah.
Never be slower than that.
Yeah, I mean, I think for analytics, the term real time gets thrown around a lot, but it really depends on the use case, right? It's a lot more difficult to do real time in a analytical setting. It's not really the limitation of stream processing tools. It's more on the analytical side, right? So we use columnar storage to accelerate analytical queries because everything's in batch, right? We store them in columnar batch, right? And that's really bad for record level updates, right? And not
Oh
really
my.
a lot of system can actually, do those kind of like second level, record level like data upserts. And
Mhm.
that is a big challenge, in the
It's
real-time
a
analytics
huge
field, right?
challenge, and
Yeah,
this is like the column versus row thing is like one of the most interesting puzzles in data right
yeah,
now. Right? Everyone's going, yeah, columns, 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 and it's like, wait, are you sure?
yeah. And
Don't get me
then when
wrong.
you try to update,
Yeah, and like Apache Arrow is this wonderful format that is flying around everywhere and has this wonderful
yeah,
IPC layer attached. You can send it around
yeah,
really easily. But it's like there's a reason Postgres is a row-based format, right?
yeah.
And like
Yeah,
it's
it's for
really
different
fun.
use cases. Yeah,
Exactly. And this is the thing, is like that exact point and we go back to our kind of earlier conversation, which is that the right tool for the right job, the right
yeah,
data format for the right job. And a
yeah,
big thing here is like we live in a mix of analytical and transactional land. So in your case, everything's a column. In my case, most things are actually a row.
yeah. Yeah, that is true. And to actually take care of this problem, like for example, like StarRocks, right? We
Mm.
have that, record level primary key index, right?
Yeah.
To take care of, to accelerate those upserts, and also in the Apache Paimon, right?
Oh
The
yes.
table format. Yeah. Yeah, almost very similar implementation there.
Mm.
So there are actually, ways to handle data upserts for real-time analytics. You can have,
There really is.
a
And
really great query performance as well as great data freshness, right? Great in terms of like analytical, right? So like five
absolutely.
seconds,
So
but not
this is
like in the milliseconds.
Well, that's the thing, right? We come back to this idea of what is real time again. And like to be accurate across, let's say, 5 years of data with a 5 second plus or minus is pretty damn amazing, to be honest,
Yeah,
right?
yeah,
And that's that's kind of the power of these systems. And as you kind of you've alluded to, there's a trade-off here. Now, a lot of analytical systems don't do this primary key index approach, which
yeah,
does mean that like when you're overwriting stuff, you have like everyone has what's known as a log structured merge tree these days, right? And as
yeah,
those kind of layers merge down, the problem ends up being is that like either you're effectively merging a whole column block with all the rows attached at once to do a small upsert. You can't do a single column merge, which is what happens
yeah,
without indexes, or
yeah.
you end up in this kind of like weird question of, wait, am I building a row system again for analytics? And no one wants that. So,
Yeah.
like particularly with Paimon.
Yeah,
So
merge on read is it works for some use cases,
yes,
where data freshness is not like in the seconds, maybe in the high minutes, it's gonna
high
work. But
minutes to
it's
up to hours, the
yeah,
number I've seen.
yeah, yeah. High minutes is it's like kind of like the boundary.
Yeah.
If you go any lower, it's gonna really destroy your query performance. Not only make it kind of slow and make it unpredictable, right? Because
And
the merge takes a lot of the
absolutely, and also expensive. Like it ruins the
yeah,
reason to use these. So we kind of
yeah,
alluded to table formats for here. So let's make sure we have our audience along the same space. These are like the lake house formats. So
yeah,
I'm sure everyone here has heard of Apache Iceberg, Apache Hoodie, maybe even um, Delta Lake. But the
yeah,
one we mentioned here has been Apache Paimon, which is kind of the fourth horseman, for want of a better thing, in this little kind of little fun bit of cooperation, as I will call it, amongst kind of the open formats. And the interesting thing here is that like this is a different way to store data. This is the kind of the compromise we make because data got very big and very
yeah,
expensive.
yeah.
Oh, so expensive.
Yeah. Yeah, it's just, it's just coming from, Apache Flink,
Mm.
it's the storage itself, it is a problem that, used to be really difficult to bypass, right?
Yeah.
So, right, you use like high performance disk, and that is something that's really, really expensive, right? And the format, right? The formats of the data that's actually stored in, right? And now with Apache Python, we have that, that kind of like the best of both worlds, right? You have streaming, you have the data freshness, you have the incremental compute, that's from the Flink world, I would say,
Yes.
the streaming world. And then you have the data governance, and you storing data in Parquet files, right? So you have all of your data as a single copy, right? You host multiple compute engines on top, right? And that's
Yeah.
great for data governance, right? And also, it runs on object storage, on Parquet files, is a lot more cost effective. So I love that, the best of the both
Me
worlds,
too.
from Apache Paimon.
Me too, because like Paimon kind of came from so if you look at the various like open table formats, a lot of like everything's been influenced by the history that came before them, right? So like if we scroll back, so big data, the term was coined by Gartner in 2001 with kind of 3 V's. There was velocity, volume, and variability. They added 3 more to make it sillier, because that's the first thing analysts always do, is they make something cool sounding and then they add too many extra words. But but it was a really kind of insightful post, because the volume is kind of a big kicker, and the velocity means you've got it's either going to be really big or really fast, but also kind of weird data. So when we get to this kind of open table formats, right, a lot of them came from the Hive world. So this is back in Hadoop days. Hive was a kind of a nice query engine to find Parquet files in HDFS. Very well thought out at the time, but with many limitations. Fundamentally, it was never meant to be real time. So as we evolved forwards, Iceberg was effectively looking at this and going, what if Hive but better in every way?
Yeah.
So they just took the
metadata.
They basically took the metadata layer and said, we're going to separate these out and say, not just storage and compute separate, but how about we separate storage, compute, and metadata? Very nice innovation, quite clever, but still just a Hive++. Then the next thing that came along was kind of like Hoodie's approach, which was, how about we put a crunching engine in there to do the merges for us, right? Yeah. And that's fine, and it can do a lot of useful stuff. But Paimon kind of decided to say, let's step back a second. We want warehouse-like performance, or at least close to. But so what do? Let's build like a warehouse and treat our Parquet files like they're level runs on an LSM tree itself. Metadata is still separate, but it kind of gives you that kind of ability to have exactly like this with primary key indexes, partial update without too much cost. And you can have a merge engine going behind the scenes to allow you to have the freshness you want. You don't have to do merge on read. You can do merge on write, or just continuous.
Yeah, that is true. Yeah, those are really exciting technologies. But, we talked about the compute, right? StarRocks or other computes, that works. And we talked about stream processing tools, right? In the center of it is, Apache Flink, right? That is a true stream processing tool. And we talked about Paimon, right? And also with table formats and storage. And that's a lot of things we have to manage, right? And stream processing, I think, despite, like Flink got a lot better in the past 10 years, especially Flink SQL. I love that now. It's really, it's gotten so much better. It's really
it's the accessibility is amazing. Like this is, I want to put my hand up and say, I'm not really the SQL guy, to be honest, but even I appreciate how good it is to provide a different interface which more people can use and really move. The performance is phenomenal. There's the running joke is it's often the most performant interface on Flink.
And so there's a catch, right?
Hand tuning a Java to be good.
Yeah, that's true. And so here's the catch, right? It's gotten a lot better, but still, with stream processing, there is still that infrastructure you have to manage, right? And that is correct me if I'm wrong, is inherently still more complex than a batch-like system, right? Batch-like, you just hit run and go and finish and that's it, right? But stream processing, you still have to know your workload really well, right? How much memory you need, right, to manage states and to those kind of things. So what do you say to that? The complexity that comes with this whole technology stack.
The answer there is that yes, there is inherent complexity in stream processing. You now have to keep a system alive, and that's never simple. Right? If I could just spool up an EC2 container and I knew it would live continuously, I'd be a much happier person. And not to bash just AWS, but put a box on any cloud and tell me it'll run continuously without input. And I think no engineer who's ever worked on call would agree with you. So stream processing requires a little more maintenance. It requires a lot more observability. It requires you to think more about your workloads. With a batch system, you know your workload when you get started. It's there. It's done. You're ready to go. You can measure exactly what you want. You can probably scale it to the performance you need. However, with stream processing, you've got to understand how much are you willing to tolerate. there are no free lunches in software, right? You always have to kind of accept the fact that you're now doing more continuous things rather than one thing. You don't have it's unbounded. You don't know when it's going to start and stop, because by definition, it's not going to stop. So there is complexity, but fundamentally, like, what you get for the complexity should be worth it. The problem with the batch thing is because one thing you can never buy back is time, right? You have to get yourself time, you must pay up front. And complexity is one of those things.
Is there a solution to this problem, to maintain such a...
So yeah, there are. So in the case here, I'm going to talk about Apache Flink, right? And Apache Flink is a bit of a beast. It's been around 10 years. Continuous evolution has happened, and that's great. Loads of new things, amazing kind of use cases, some really, really, really clever people. It's been a lot of effort making it amazing. But once again, if you are not wanting to have to maintain a team of people to maintain one of these services, that's kind of why people like us exist, right? We take these big complicated systems, we tune them to be suitable for people like ourselves. So in our case, what we took Apache Flink and we made something called Vera out of it. Now, Vera is the Ververica runtime assembly. The goal here was to say, Flink is amazing. So many innovations, 10 years of evolution. It kind of needed a bit of a revolution at the end, a bit of a cloud native one, to make it possible for us to offer it as a real service. Now, the goal of Vera was to basically say, 10 years ago, Hadoop was still a thing, a big thing, in fact, right? And we want to remove all those annoying dependencies. We want to put in all the hooks you need as an operator to be able to have like the actual control you need, but also to kind of remove some of the existing limitations. So the three kind of pillars of Vera are streaming data movement, the ability to pull data from wherever it is and be able to act on it, real-time stream processing to give you an upscale on there. So this means your state store is now flexible, it's faster, and it can have tiered storage out the box. It's disaggregated state plus, and the ability to then do larger than memory joins in stream as well as post stream. And the last one is the stream house. This is where we kind of said, like, Flink needed more than just big state on joins. You wanted to have that kind of streaming lake house or stream house. So we actually integrate Apache Paimon from the get-go, giving us the ability to have a real-time lake ready to go along with your queries, and then kind of give you some kind of usability on top of that. So like the key things that often come out of this are like customer 360, because whenever they call up an insurance company, can remember their policy number when it matters, right? Because I can't. So the ability to have this unification with no real limitations on the storage, no limitations on the state itself, and no real limitations on where the data comes from. This just takes what you do. But to be kind of really clear here, this is still Apache Flink. We don't give you a magic compiler. There are no magic extra codes. You write, if it's a Java job, you write your Java job on normal Flink, and then you compile the jar and you put it into the platform and it runs. If it's a SQL job, build it as you would. We only give you like 2 extra key things you can do, which is the ability to create whole database, like whole warehouses out of databases in one go. Like particularly works really well with StarRocks. So if you want to ingest like whole MySQL clusters into StarRocks, with one statement, you can dynamically create all of the destination tables, have all of the data continuously synced over, and for any transform you need in flight. And I could talk for about 4 or 5 hours on this, but like we've got a bit of a white paper here. The link will come in chat, and this is just like what it took to get a cloud native version of Apache Flink in a way which is easy to manage.
Yeah, that is exciting, to take off the load, of the user, and actually, to get them to focus more on what they're building, right? It basically stream processing jobs, and to manage their data and to query the data, to get that business insight, to serve their customers. That's what they should be focused on, right? So it's very available now.
It is. So currently Vera is available on our managed cloud service, and will be coming very shortly to our on both BYOC and also on our self-managed offering. Part of the unification we're doing here is not just, so Flink famously unifies batch and stream processing, but we're trying to also unify the fact that like often a lot of people who have to run on their own metal or on their own cloud have been a bit left behind by like this kind of cloud native thing. So we're unifying it across the board. So going forward from a certain point soon, every offering you get from us will be running on Vera rather than an open source variant. Yes, we have previously done a lot of work with hardened, versions of the open source, but to kind of make it truly kind of performant at scale, we had to do a lot of work. And now we want to make sure that is what people get from us every time.
Yeah, that's terrific. It's on Ververica now. So good to hear that the demo I built, we're gonna show a little later, is on Vera, right? We're gonna be able to see that very soon. So yeah, we talked a lot about a lot of theories, right, about what is stream processing, and we talked about the complexity of stream processing, right? We probably spent a little too much time talking about like the complexity of stream processing and the use cases, right, where we can use stream processing for transactional workloads, transactional, operational streaming, right, and also with customer-facing like workloads, right, where you directly serve an end customer, right, that extra data freshness is going to provide you with so much more value and put you, so much ahead of your competitors, right? And all of those are actually available today. All of the theory we talked about today, they're actually available today. And so here I'll take over and I'll do a demo. So yeah, so a demo between CelerData and Ververica. So CelerData is a managed version of StarRocks, and Ververica is, what is on Vera. So it's a managed version of Apache Flink, right? So here a little introduction of StarRocks and CelerData, right? StarRocks is a real-time data warehouse, right? That's able to do a lot of things, right? It first has a very simple architecture that's with no external dependencies, right? FE and PE, those are FE and CN, those are the two kinds of processes that's there, right? It runs on a MySQL interface. It can do joins on the fly without the need to actually denormalize every piece of data that you have, right? To put too much pressure on Flink.
That is a big deal. Denormalizations are hard to get right.
Yeah.
Multiple copies of data in lots of places, and it really slows down the end result.
Yeah, and you think about, schema change, right? You have a dimension table that joins with a really big, like a tens of billion row fact table, right? When you do a schema change on the dimension table, you actually have to like backfill all of the data, like the scale of your fact table. And that is not something that you want to do. We actually have user that, runs a metric system, right? Because they were using Druid, and they had to do denormalization, and a schema change can take up to like 2 days because of the data backfilling. They have like petabytes scale of data. It's too expensive, and it's not anything that that user have to should ignore, right? And so first is join, and then it's data observes, right? Data observe really comes handy when you're trying to sync your data from a transactional database, right? And that's where you can use Flink and StarRocks together, right? And here is how the demo is architected, right? So we're gonna have a Postgres instance running on the VM, right? And we're gonna use Flink CDC to Flink Ververica to read the change log of the Postgres, and then we're gonna use the StarRocks Flink connector to directly sync all of the data, all of the changes from the Postgres instance to CelerData Cloud, which is based on StarRocks, for basically faster analytics, right? And so here, let me share my screen. Can you guys see my screen now?
A live demo for everyone on Zoom.
Yeah,
everyone cross your fingers. It should be good.
If it doesn't now, I'll record another one.
Yes.
It's gonna be fun for you guys, should be. So here I have a Postgres instance running just from a random VM, right? And I have a table here, right? It's a empty table. And here is CelerData Cloud serverless, CelerData Cloud POLC, right? So this is the flavor of the CelerData Cloud that runs in your own VPC, right? With StarRocks, the enterprise version of StarRocks running inside of it, right? So you can, so you own all of the infrastructure and you own all of your data, and we do the maintenance kind of from remotely, right? So here's the demo, right? So I already have a table here called weather, right? The same table as the one in the Postgres, right? Both of them should be empty. Let's take a look, right? Both of them should be empty. And here I have a job that a Ververica, a very job, that reads the change log of the Postgres instance, right? And then sync that to StarRocks using the StarRocks connector, right? And here we can see the lineage, right? And here we actually have a columnar level lineage. So Ben,
So
can you
just jump in
shed a
on
little
this
more
one.
insight on
This
that?
is
Yeah.
this is one of those features I want to call out a bit of, because Lineage is classically just I move data from A to B. So I know the source table, maybe I know the destination table, but often, like particularly when you start doing the cleverer stuff in analytics, and when using CelerData, you really will be, like, you want to know where that ID field came from, because you might have joined on a different one. Let's say you do a couple of joins and there's an ID field, there's a customer field, and there's a date field. You don't know what date that is. And the lineage trace here lets you know where that came from. Maybe it was the creation date, maybe it was the sale date. And particularly when you need to do that kind of governance feature, or in this case, like, just want to really be sure you're actually doing the right kind of thing, you really can do a lot with columnar level lineage when you want to see, oh, so this is my pipeline. I've joined, in this case, city details. Maybe I've added in some traffic details. Maybe I added in some weather details. And you want to know that each of those fields came from the right table at the right time.
Yeah.
Meaning that any decision you make, you can trace back to where it came from.
Yeah. This is really cool. And now this is running, right? It shows this is running status.
Mm-hmm.
Okay. So if I put in a insert into here, let's do New York. I feel like New York today. Okay. So now we should be able to see the one here, right? In Postgres, of course, we just inserted it. But we should be able to see it here. Here we go. So what we just did was we ingested a row of data into Postgres, right? And Ververica read the changelog, was monitoring the changelog of Postgres, right? And sync that data into Ververica, and then sync it to StarRocks, to CelerData Cloud, right? And now we can do another insert. Let's just change that to 28th date, and let's do that again. And within 5 seconds, that's how I configure the checkpoint interval. And within 5 seconds, we should be able to see it right here. Okay. So yeah. So this is a really easy way if you're trying to do analytics on your transactional data, right? And because CelerData supports second level data upserts, right? Even on massive amount of data powered by its primary key index, primary key record level index, right? And so you can absolutely sync all of your changes from your TB database and still get great data freshness, right?
To give a fun example of why this is really cool. So a classic use case is the user-facing dashboard, right? Yeah. Let's say you're an e-commerce vendor, or or even a hotel vendor, right? And you want your users to know the status of their trips at any given point in time, their points balance on their loyalty cards. Now, as you take an action, particularly, airlines are another one. Sorry, big on the brain. I'm right next to the airport here. I can literally see planes out the window. If you want to know your actual balance on your points on your air miles, right? And you want to see that now, I pay for my flight. That goes into some OLTP database, probably Oracle, because they've not changed in a while. Well, to be honest, Oracle works great, just as expensive. So then you want to sync that over live. This means as soon as you leave that page on payment and then go to your balance, you'll be able to see that immediately at any scale. Firstly, this is using the Vera engine and the streaming data movement to move it to where it needs to be immediately. But then using the power of StarRocks and CelerData, the scale, it doesn't matter anymore. You can have 1 million users hitting it repeatedly and not have to worry.
Yeah. And another thing is, it's the ability to do joins, right? So, in database schema design, like normalization is always always been the best practice until we started thinking about analytics, right? Because drawing is such a expensive thing to do. So for the past, like I would say 10 years or even 20 years, right? Denormalization was always kind of like the false best practice for analytical workloads. And we say no to that, right? We try to make drawing run faster so you don't have to go through denormalization pipeline for all of your data, right? You should only do denormalization for those that requires extreme performance, right? So that really, so you can basically keep the same schema as your Postgres, between your Postgres instance and your CelerData Cloud instance, the same exact schema, right? And run joins on the fly, and that really helps with your data pipeline, simplifying data pipeline, right?
Cool.
And so this is my demo, and I think that is all we have. And yeah, so now it's a great time to take questions. So I actually have a question first I want to ask. What should you use Apache Flink for?
Oh,
sorry
gosh,
for asking that, but what
well,
shouldn't you?
this is a good question, because like we kind of pride ourselves here in knowing where you really shouldn't use that tech as well as where you should, because it's so easy to get sucked up in the hype and think, oh, I need a thing, I need a thing, I need a thing, and then everything becomes the hype train again. So there are a lot of cases where if you need, like where Flink starts to not make sense. Now, Flink can do a lot, and I'd love to just say there are none, but when you start looking into your actual layout, there's a lot of CRUD type systems where, one, Flink doesn't have a web server. Flink pulls data from A and puts it to B. So you cannot really, data doesn't really start and stop in Flink. So you still end up needing some level of API gateway, some kind of like microservices, and certain types of business logic don't really fit Flink directly. The other big thing here is that Flink has interfaces for Java, Python, and SQL. If these are things you don't use in-house, like I'd argue that though it's worth bringing in Flink anyway for some jobs, it does mean there are certain types of things you probably wouldn't use Flink for. Next thing is also that although Flink is a soft real-time system and gives you very fast performance, if you're getting into the high-frequency trading type spaces where you start counting micros and even nanoseconds, there are other tools for this. FPGAs are amazing. But so if you need to go at a true crazy scale of speed, like true crazy speed, don't use Flink. If you also, like, there are also plenty of jobs where, like, you might just get away with the database. Like, there are like, if you just have large, if you're being shipped, let's say, a terabyte of data every 3 weeks from, a vendor, right? Just use StarRocks. It's fine. Do a big query on it. You could ingest it with Flink. Yeah, Flink can do batch queries, but it's overkill for that in most cases. Also, when you're below a certain scale, and you don't expect the scale to change, like an internal job, right? Spinning up a Flink cluster, even a serverless one on Ververica Cloud, could be overkill, right? Like Flink excels when you need continuous, or even the batch side of Flink. Like you tend to want to use that once you already have the stream side of Flink running.
Yeah. Thank you for the answer. Thank you for answering that question. And now we have some questions from the audience, so I'll read them out. So first, from Chris, does Lineage work with custom Flink jobs or only with Flink SQL?
So the answer is it works. So we've got a couple of data stream examples on which I've given before where the data stream Lineage does work. There are limitations, right? So Flink SQL kind of has the table API ability to know what all the types are at any given point in time. So the fields come through. If you start using data stream jobs, like you can almost do anything. And particularly if you kind of step away from standard serialization, we can't trace it in the same way we could, because you could literally rename a column inside your SQL, inside your Java, and you wouldn't be able to know what's going on. So so you could follow up. If it does, how does it inspect custom code? So it doesn't inspect your code directly. What it does do is, particularly on the table API, is your serialization is known. And if you're using a serialization to a known format, that is also known. We do not inspect your code. So at table type level, we know where your data got pulled to and from. We know which operators it went through, even on pure data stream, pure Java, right? So we'll be able to trace through those, right? So we'll know you pulled this block of data in here, this block of data out here, right? But that's at a table level. So we know, let's say you pulled a customer table in, we'll know the table went through all these steps. We can't tell you if you used how much of it you removed or didn't remove, but we'll know it went in. Part of the reason why, like, at least for transformation pipelines, SQL is often a good choice, or even the table API is a good choice, is because of this Lineage feature. When you start doing the transactional jobs, Lineage starts to fall away when it comes to its actual impact and usefulness. Hence why, like with most people writing custom Java code, Lineage is something a bit more complicated. There are ways to get around this, but that specific tool you saw there is mostly based around kind of table API thinking.
Yeah.
If you want to go into more detail, like send me a ping and we'll happily talk through it in detail of one, how the actual tool works behind the scenes, but also like if Lineage, particularly on custom Java type stuff, is of issue, there are some really kind of good techniques from like OTel type thinking, which is really kind of useful to work out what data went where. But also then you can trace most serializations through Flink anyway. So it's really just a matter of like, what do you really want it to do? And please don't use cryo. If you use cryo, all bets are off.
Okay, next question. So how do you get the first batch of data in there before you turn on streaming? For example, a MySQL database, Flink StarRocks. What is the best method to get all of the historical data in there? I think I'll take this one. I think I'll take a stab at it first. So I think one way, you can use a MySQL external table and do an insert into, that can handle a pretty big chunk of the data. I think that's what a lot of our user do, especially, right? And Ben, do you have anything to add to this?
So yeah, like to be honest, that is a pretty good way to get started, and it removes a step. If you've got the Vera engine next to you, there's a thing called create databases select. So I can, with one line of SQL, just mirror the whole thing over. So behind the scenes, the CDC connectors for Flink are built out of Debezium, which has both scan and kind of bin log capabilities. So it will do a scan to the end, then bin log off the bottom. So it will just sync the whole table over, plus DML and DDL changes. So you can do both a snapshot plus continuous. But to be blunt, once again, if you just need it there quickly to do some work on, just use a foreign table and go.
Yeah, and also, and does that take a lot of resources though? What you described in with Debezium?
This is why doing CDC is so powerful. CDC as a bin log or as a write-ahead log from Postgres or equivalent is really low resource on your actual OLTP database. The big thing here is that if you do a big scan, you're going to put a lot of load on your database. Simple fact. If you are doing it continuously, you're going to put a lot less load on. Yeah. Like reading the write-ahead log from Postgres is almost free. So there's a reason why CDC is important, and particularly if you don't want to have a massive, like a latency spike on your main database, which is processing your actual online transactions. This is why you use CDC. But on day one, you just need to do something quickly. Sometimes you're willing to pay that price.
Yeah, makes sense. Next question. Data lake analytics has become more interesting, but it seems like there's still too slow to really support streaming/real time. What does the future look like for streaming analytics if people are moving toward data lakes?
So
open formats.
Yeah, open formats are starting to really, the problem with open formats is they kind of showed us what we could really do. They kind of opened the door to this thing could be faster. And as soon as things could be faster, they had to be as fast as possible. And like part of Apache Paimon's big strength is that almost real-time data lake, or the stream house as we call it now. So rather than just the lake house, it's the stream house. And you can do streaming joins against Paimon. Though that still leaves this gap because it is accurate to seconds and single-digit minutes. You can still go faster. So there's something being launched called Apache Flux quite soon, which is kind of that intermediary layer now. So you have now got, so it was announced at Flink Forward last week, and it'll provide a kind of that intermediary layer between big scale open table formats, your in-process memory, which is ultra high speed, but that kind of middle layer of streaming for storage.
Yeah, makes sense. I think talking Flux is probably, the answer to the next question as well. So from the Paimon's perspective, what do you think is going to happen to the space, especially now with Snowflake doubling down on Iceberg and Databricks buying Tabular?
So we're into a really kind of odd space now. Honestly, I didn't expect Databricks to buy Tabular, though.
Yeah.
Though I know some people at Tabular who were very excited to join forces in a big way. So
Yeah.
the key thing that I see there for Paimon is it's all good. This is very much a space where like adoption we're still early days in adoption of these formats. So having the rising tide and the big players putting their weight behind these things is a good thing. Paimon is actually going to bring out a Iceberg snapshot thing, so you can query a Paimon setup like it's an Iceberg setup to allow for that kind of cross compatibility. There's also things like Apache Xtable, which are bringing these open formats together in a way you can have a bit of interface between them. Whether or not that takes off is an open question. It feels like adding an adapter, like one of those multi-plug
interoperability is it's a big, but it's very difficult, right? Because every table format is, table formats are built to solve very similar problems, as with just Hive, like poor metadata, no ACID, relying everything on the file system, right?
Yep.
But they're so different, they're features that are in Hoodie, they're also in Delta, they're also in Paimon, but they're built completely differently. So like have the road toward that interoperability between formats is still people are still working on it, right?
Because like there's a whole massive thread about atomic compare and swap, and being able to do that to get these ACID guarantees on your lakehouse. And yes, a lot of these like various formats have built an answer to it somewhere, but then they rely exactly on the file system, or they rely on like some sort of file-based lock, or they rely on S3 and Hope, and it's a bit messy. But like, they are solving a similar problem. They just came at it from different angles for different reasons. Like Hoodie was about reusing existing tools at Uber. Iceberg came from the fact that Hive just failed at scale at Netflix, and Paimon came from we need to go faster.
We do need to go faster.
Crazy.
Yeah, we do need to go faster.
Yes.
And next question.
I'm an impatient person, so I'm very much in the Paimon.
How do you make a streaming solution compatible with the transactional database like StarRocks? StarRocks is not really a transactional database, more analytical. As far as I understand, doing inserts in StarRocks generates both partitions and replicas. And I see a potential issue where frequent small inserts are made. Streaming solution compatible with StarRocks.
Ooh, I can start with that if you like. So Flink and StarRocks actually have a very kind of close relationship. Like I think in some respects they were developed kind of right next to each other in some cases. So StarRocks was actually originally developed next to a Flink solution. And the key thing here is that like if you look at some of the alternative data warehouse type setups, batching is a big deal, particularly on ClickHouse. ClickHouse would love you to insert 100,000 rows at a time every time, please. Otherwise it starts to eat the performance. StarRocks came from the kind of a bit more of the, should we say, pragmatic world of data will come as it comes. And the reason for separations between front ends and back ends is that ability to internally deal with batching. And have more pieces to go for. You'll realize I'm quite a fan of StarRocks as well.
And not with inserts as well. It's inserts and upserts. Upserts and deletes are some of the even more challenging. Problems for analytical
deleting is
like
weirdly complicated, isn't it?
It's just it's just real time upserts and analytical. It doesn't go right. One is like row level, and one is like column level, and row view versus column view. And we just talked about that, right? And there are innovations that we're trying to make, to make so the user can have sort of the best of the both worlds, right? From the analytical part and the real time like record level upsert part, right? And we are working on those. Next question, I think the final. Oh, there are more. How does Flink/Ververica deal with scaling? Like when a bunch of data reach the initial PostgreSDB and resource sharing, can I run 3 small jobs on the same cluster/VM, etc.?
Okay, so to do them in reverse, because the second question is quite easy and plays into the first question. So Flink has kind of two main modes: application mode and session mode. A session cluster is a shared cluster. We run n jobs on it. Do I recommend that for continuous online operation? Not always. It's really good for when you want to do exploratory work, SQL things, or you're trying to do that kind of more batch style workloads on Flink. Flink and Ververica specifically also support a lot of the kind of like the gateway connections. So if you want to use Flink as a one-shot transformation engine where you just want to convert data from A to B, you can do that via JDBC into Flink directly, and that's where session clusters come into their own. There's also that piece when you're just doing one big crunch, whether it's Jar, whether it's Python, whether it's maybe a machine learning task where you're training a model. That is where like session clusters come into their own. But application mode is where you normally want to be for long running tasks. There's no reason you can't, but fundamentally, like you'll run into the simple fact that the scaling parameters for one job are going to be wildly different from the scaling parameters for another. Like, yes, there's more overhead in having many application mode things, but your SLAs are going to be better. So you get what you pay for, in my opinion, and it's worth it. The second thing about it was mass data hits Postgres. So this happens all the time, where someone goes and changes half the table. So there's 100 million wall entries smash into a Postgres wall. How does Flink deal? Now, there are a few different ways. The first one is reading a write-ahead log can be done in parallel. Particularly as you get multiple table type things, so you can read that way. But versus like, let's say, a Kafka Connect model where a task will just explode when the JVM runs out and then take out all the versions next to it, Flink ingress is reasonably well sandboxed. So that will just run. It will take time to actually kind of synchronize fully because there are no free lunches. Like if you put 100 gigabytes of data on your wall, we will take a few minutes to read that, or seconds, depending on scale and network bus between the two. Remember, networking is never free. Even on AWS's backplane, you still feel the cost and speed of the network. So the short version is it won't explode. It just depends how big your machine is and how much scale you've put behind it. On Ververica, particularly, and on Vera, you can specify a SLA to scale to. So one of our autopilot features is to scale to an SLA. So you say, I want my downstream pipe to run inside 30 seconds. So we will increase parallelism of your job until we meet that SLA, if we can. So that's kind of how we do it. In open source Flink, you just put your autoscalers against like some level of CPU, and you'd hope that the ingress task would actually kind of spike out, the back pressure would build, and you just go from there. Flink itself will not explode. It does back pressure at every single operator. So you're never going to explode a downstream small thing by having too much upstream data.
Okay, thank you. I think that's the last question we have. And any more questions? I think we're way over time. We scheduled for
a little bit over,
minutes. It's 70. It's like more than double. But I definitely had fun. I learned a lot from you. Yeah, I hope you guys too. I hope you too. And I hope that was a good experience for you and the audience. If you have any more questions, please ask them in the Slack. Be sure to join the StarRocks Slack channel. You can see it there, right?
I'm there as well, I think. I might have to change my... so actually, I think I might have to log you back in on a slightly different account, but I've definitely been in the StarRocks chat for a while.
Yeah. And the Flink technical white paper, be sure to check that out, right? It's a really good read. I learned a lot from it. Thank you, guys. Thank you, everybody, for joining. And see you guys again in the next webinar. Thank you, Ben. Thank you.
Thank you very much for having me.
Thank you.